Okay, hello, welcome back to another video recording session where I talk about genetic algorithms, the very basic stuff. Today the date is 2025, March the 5th, and well, yeah, and today the notebook I'll be going through is this genetic algorithm grid search 2, and the purpose of this notebook, this notebook is to assess the impact that number of entities in a population has on the evolution and effectiveness of entity generation, with a population of null entities that contain nothing to begin with, or void genes. So in other words, I'm just going to be testing how different sizes of population affect the overall outcome or overall performance of entities at the end of the evolution after a certain number of generations. Mostly it's just 3,000 generations, but we'll see. And again, as just like the last time, I won't actually be running the cells here. I'll just be going over the results that I got when I ran it previously on my Mac. So because it simply is going to take too much time. So here we go. So first off, we import all the things we need and the items and the values and constraint lists. All these lists are created. They are still the same as before, so nothing different there, nothing unusual. All the functions are also the same and the hyperparameters are also the same. Well, the ones that actually matter or that I use are mostly the same. Max constraint, the weight threshold being 4,000. Number of items is still 20. Mutation rate is still 3%. Yeah, that. And generations and population size will be changing within the for loops. So what again, I start off with creating the void gene and the genesis, or the initial population full of void genes. Yep. And I start off the evolution. The first part, step 1, or phase 1, stage 1, is again evolve for different numbers of generations. For how many? For 20. For 20 entities in a generation. And once that is done, draw the graph. We still see it oscillates, but the key takeaway here is that this is at a significantly lower score, at a significantly lower score level. These are the scores of top 20 and, well, average of top 20 and top 30 entities, and they're still at 500, and top 20 is at 500, top 30 is at 460, 50 or 60, which is very low compared to the ones before, where it used to be around 600. So we'll see why in a bit. So that's so we go on to the next one, but we evolve for 3,000 generations with 20 in the population. Is it just 20? I don't know. Yeah, well, it could be. And this is what happens. The thing is, I start off the one thing to remember is that I start off with top 20. I start off with 20 entities in the population, but as it goes on, there is where is it? This bit where in order to make up for the lost ones, I keep the population 1.4 times the initial population. So if I start with 20, I'm going to keep getting 28 entities in total. Same for this. So I evolve it for 3,000 generations, and I run it, and I run that 10 times. I do that 10 times, so that would be not 5 times actually, 5 times, because it says 5 here. That's also another typo that I forgot to change. It's not a typo. Well, is it a typo? I don't know. And that took 8 seconds, so which is very long, because considering I only have 20 entities or 28 entities max, and when I do that, it still oscillates. But here I see that I'm still getting nowhere close to. I think this is for a different number of number of entities in the population, but the point is it's still nowhere near what it used to be, which could mean that if the population size is small and keeps and is kept that way, not enough mutation happens, and because we're starting with void genes, if there isn't enough mutation, it just means that there will be no initial changes for the better. Again, it's a very subjective word, but very little room for change for the better. So yeah, and when let's evolve something for a very, very long time, 30,000 generations, and do that once, and here is the plot. Still nowhere close to 600, when we know that 710 is the max. And we do it again for 3,000 generations, but do it 10 times, and then when we plot it, this is what we get. So this is still the same thing, and this is still the same thing. And let's try for 3,000 generations, but with different numbers of numbers for the population. So we start off the smallest population, which is 10, and then there's 50, and then there's 100, 150, and on and on and on and on. So 10, 50, 100, 150, 200, 250, 300, all the way up to 1,000, or 500, and then we increase by 100, so 500, 600, 700, 800, 900, and then 1,000, 1,000, and then from 1,000 we go on to 2,000 entities in a population, and we do this how many times? Yeah, and we do this 5 times. So we take a population, evolve it for 3,000 generations for 5 times, and then we move on to the next population number, and on and on and on and on for 17 times. And this took, well, on my Mac, 2083 seconds. So not short. And this is how it went, but this is very hard to decipher. And this is how it went. Sure, again, it's still very hard to decipher. This is what it looks like until generation 30. This is what it looks like until generation 50. This is what it looks like until generation 70. this is until 100, and then this is until 300, and this is until 500. But one thing to note is that let's look at until 300 or 100. Yeah, 100 seems. No, 300. Let's look at this. Until generation 300, the lowest the lowest plot the lowest plot is for when the population is at 10, and the highest one usually shows the steepest climb in the score, in the quote-unquote score, the average of top 30 entities, and they quickly plateau and then kind of stay there. They still do, it still does oscillate, but a bigger population just reaches there a lot more quickly, which is obvious because the more you have, the more likely it is for you to get more entities that are relatively better, and they also get to procreate and reproduce more, and then adds up. Of course, there is still something that I need to talk about in later videos concerning this, but as far as this notebook is, this Jupyter notebook is concerned, yeah, that's all I can say. Another thing is that all the ones that come right, above, is this. This is when it was. This blue line. Blue squiggly line is for population 10. This orange one is probably for population 50, and then the one after that is probably for 100, 200, 300, 400, and on and on and on and on until 2000. The one at the very top, which probably is this pink one right here, or it could be the red one. But it seems very most likely that it's the pink one. Yeah, I think it is. This grey one is the pink one here. Yep. This blue one is also the pink one. So the key takeaway here is that more population certainly does help. Then again, you can't have an infinite number for population, because that would just be too computationally heavy, and that's not why we're doing this. If it's too computationally heavy, then well, it would still be better than brute force iterating through all the permutations and combinations, but still it'd be nice to know a number for the right number of it'd be better to know the right number for a given number of population, if that makes sense. 10 is definitely not it. Even when given 3,000 generations to evolve, 10 is not the way to go. Never. It just never reaches that. When given this simple algorithm for choosing the parents for procreation, if the initial population is small, it will just not perform. Yeah, so that's about it for this video. See you soon.